Hello, how are you? You guys can hear, right?
Yeah, I can.
Okay.
Hi.
Hello, welcome. Yeah. So we're going to start in a minute and waiting for Kevin. Here.
Kevin's not here yet.
It's okay. We record for him. So as you can see, this is a week 11, lecture B. From now on, I hope you will look into week 11 notes. You are going to see that week 11 notes. You're going to see John Bay, this chapter 7. John Bay, chapter 7. Okay. This one, chapter 7, system stability. This is a very nicely written chapter on all the stability in the state space setting, linear time invariant systems. But today we are going to go through this deck of slides. Can you see? I think you can see. So let's go on. Let me see if I can write. Yes, we can see. We can write. Let me do one more time. Pen. And how to change the pen color? Pen, ink color. Ink color. Okay, we're ready to go. Okay. So it's a John Bay's textbook. It's very well written. So please do read them. Last time we covered mainly on internal stability, uniform exponential stability. I put more emphasis on the uniformity, okay, the uniformity. Okay, when we see uniformity, meaning you have a delta, you have epsilon, okay, and then these things are not function of T0 at all, okay, it's not function of T0 at all. So that's called uniform stability. I do have examples about uniform stability and stability. What's the difference? So let me see. Yes. Okay. So let's just quickly do that. What is the uniform stability? Meaning, if your initial state is in this ball, then your all trajectories for all t will be within this ball. So this is stability in the sense of Lyapunov. Uniformity means it's nothing to do with T0 for this, okay? But remember, epsilon is a function of delta, okay? Okay. On the other hand, you can also say, if you want x within this ball, then you can always define your starting initial condition within the delta. In this case, delta will be a function of epsilon, okay? So regarding exponential stability here, that means you can be bounded by an exponentially decaying function. So lambda is positive, okay? So it's a exponential decay. So this is the size of your initial state. And there is another gain, gamma here. So if you can find gamma and lambda, you can make all the trajectories, state trajectories within this. Then we call this is exponential stability. Okay, so we have seen here is S, US, ES, and UES. Okay. Last time we talked about another one is called global. So for linear system, global and local are equivalent. So whenever you say stability, it's global stability. Okay. But for nonlinear system, it's not true. Okay. Everything is supposed to be local, unless you can prove it is global. Okay. So we connect the stability with transition metrics, state transition metrics. So this is a notation of if and only if. So it's called if and only if is IFF. This is a term, IFF, if and only if. So then if you can bound your state transition matrix like this, then it's exponential stability. So this is kind of a definition about stability. The reason we use the term here, internal, means we didn't apply any external input U in there yet. So it's intrinsically without control, it's still stable. So it's called internal stable. So we introduced Lyapunov transformation, P inverse bounded for all T. So we find out the internal stability will not be changed. So today we are going to do some test. So so how you can check? People say, oh, how you can check the stability given the state space model? So what's the definition? How we can check? What is the sufficiency? What is the necessity? Okay. So with time allowed, so we can go through some examples. Okay. So Lyapunov stability. State are physical variables. So any physical variables, the square of the signal is actually related to the energy. Okay. Let me give you an example about why we say that. So you have R. So you have a control signal, give control in here. So the signal in here is either V or I. Okay. So we know that the energy inside here is I square R I square I, or is V square divided by R, or I times R times V. Okay, so these are the two, three. This is by definition. Okay, by definition. So you can see this all kind of square. Okay, it's a signal square. So therefore, we say the square related to the energy. Any signal, whatever signal, you say xt and xt square, that's related to energy, okay? So whatever. So if you have a capacitor, the voltage is V, then C times V square is the energy. Inductor is the same, and velocity is mv square, for mass spring damper system. So basically, we are mostly commonly used dynamic system is called MSD, or mass spring damper, okay? Or we do LRC, okay? Like inductor, resistor, and capacitor. So then you can all find out the energies linked to the signal square. So the idea why Lyapunov is so great, he invented the concept of abstract concept of energy, or the energy. So if somehow the energy of the system decreases, then the system will not blow up. So that's called a stable. Okay, called stable. So the energy is bounded. Okay. If the variable is bounded, of course, it's a square, right? So it's not 0 if variable is not 0. If it is 0, then variable is, so it's a positive. And it becomes 0 when the variable is 0. So it has to be smooth, so you don't have a jump, okay? Smooth. So meaning it's differentiable. And signal square is differentiable at least, right? So now let's talk about the LTV system without control. It's called homogeneous state equation without external control. So quadratic Lyapunov function is a function of something like this, okay? Rn, so I think this is Rn, okay? To a R, meaning this is a scalar, okay? This is a scalar. It's an indicator of energy. V is indicator of energy. So this is for the generalization, meaning the worst case is I, okay? When n is 1, when n is 1, then this is x squared. As I said, x squared is linked to the energy. So this quadratic form is a vector form of a square and with a weight of q, well, q is positive definite. PD, okay, positive definite. So then this quadratic term will always be greater than 0. So we also put the Q is symmetric and positive definite, okay? So we allow this, it's bounded by, this is a constant, okay? It's bounded by the norm of X, okay? Okay. So this is called bounded. And also lower bounded by, this is upper bounded, it's lower bounded by a quadratic as well. So can only decrease if the state decrease not too fast. So therefore along this, this is a scalar, remember, this is a scalar, and the change over time is continuous. And this change at all the x trajectory is less than 0. So all these are quadratic Lyapunov function is a generalization or abstract energy concept, okay? So this energy, by these assumptions, it will be decreasing, okay? If I can find out quadratic function like this, and we can prove all these properties, then I know that the system is stable, okay? Does not increase along solutions. So this Q, okay, this Q is definitely is less than this one, means the Q is a diagonal less than this one, okay? So if this one, that means the Q are greater than this diagonal. This is diagonal, okay, diagonal. Okay. Remember, when we say something, this is a matrix, is an n by n matrix, less than something, we should understand it's Q minus rho I. So move this one this side. This is a matrix n by n. This less than 0. This then or equals to 0. This actually is called NSD. Okay, negative semi-definite. Negative semi-definite. Okay, so that is when you write this matrix less than this one, it's not a, you know, this is maybe fully populated, this is diagonal, how you can compare. No, it's actually understood in the way of NSD. So the difference of the matrix, this matrix is negative semi-definite. So same thing we should understand. This Q minus eta I, this matrix is positive semi-definite, okay? So it's a Q minus eta I is positive semi-definite. The reason we have semi means we have an equal sign here, okay? Equal sign here. If it's strictly less than, then it's called a negative definite or positive definite, okay? And V is continuous, as we can see. In other words, if I can do dt is continuous, okay, continuous. Remember, the Q is given by you can pick up, okay? If the Q is a constant, is this continuous? Of course, yeah. So this is a more general, okay? So in other words, it's also equivalent to that, this is my V, I remember, this is my VT. So if I do a DDT, we have how many terms? So we have the first term, DDT, QX not change. Then you have a keep this one not change, we do this. But we do have another term, so this is due to Q, this is this one. So you have three terms. Remember, if Q is constant, this is 0, okay? This is 0 if Q is, so this term will be 0 if Q is constant. But that's not the point here, and we are going to, because we know that x dot t is ax, so x transpose dot t is x transpose a. And I have q and x. So this is another one. We copy this one here. We just copy here. This one we have x transpose q and x dot is ax. Okay, ax. So we do a right multiplication, pull out. What's left is a transpose q, qa, and this one. Okay, and this one. So to make this v dot, so remember, this is v dot, okay? This is v dot. We want to make the v dot less than 0. It's not increasing. This is always decreasing. What does that mean? That means this whole thing inside the bracket, this whole thing has to be less than or equals to 0. So it's NSD, okay? NSD, okay, NSD. So you can see that if we choose the V as a quadratic, like x transpose q x, so to show that V dot is not increasing, then end up you show this is not increasing. Or what does that mean? What does that mean? So remember, V dot is dependent on my x, okay? So depending on my x. So, but here, do you see any x in here? You don't see any x in here. In other words, you don't even have to solve this x dot is ax to get an x to check the v dot x. So you only need to get using a and put out q and define this. So that's the beauty of Lyapunov function. So you can decide if the system is stable in the sense of Lyapunov without, listen carefully, without actually solving the original ordinary differential equation. Without solving it, using this equation, you will be able to tell the stability because they are equivalent. That's the whole beauty of Lyapunov approach. So with that, we can have a theorem, summarize what we said. If you have a LTV system, it is stable in the sense of Lyapunov. If you can find a quadratic Lyapunov function, okay, it is increasing, and also the V keep going down, okay, decreasing, okay, decreasing. Then the system is stable. So let's make a proof of it, okay? So we assume I got a V, it's quadratic form, and satisfy the condition that it is bounded by two, so the V is bounded, V is positive, we don't have to use this one, absolute value, okay? So basically you don't have to use you just say V, so V will be bracketed, so less than, like rho I greater than like lambda I, okay? So then this is positive always, and we assume the Q transpose Q is Q, so it's a positive, it's a symmetric. So that qualifies to be a Lyapunov function. So you start with the initial state, the initial time. So then we check Vt minus Vt0. So then this is Vt, this is Vt0, okay? This is Vt, this is Vt0. So we see whether this will decrease, okay? Will decrease. So then we can write this one in terms of derivative. It's a derivative of the sigma here. We don't need another sigma here. So we don't need a convolution here. We just say this is a derivative. So it's a t minus t0, right? T minus t0, so it's exactly the same. And this is less than zero, less than zero. And remember, this is nothing but the V, okay? This is nothing but the V, okay? So then we can say for any t, okay, for all t greater than or equals t0, this is always true, okay? Always true, okay? But on the other hand, Vt is lower upper bounded by rho, okay? Lower bounded by eta, I use eta and rho. So therefore, so there's a lower bounded. So therefore, we have the x norm will be always less than x0 norm, okay? So in other words, I can always, for all the solutions, will be bounded by this, okay? Bounded by this. By doing that, you can use now epsilon delta language, okay? So obviously you can write this is, you can use challenge and respond method. Say, oh, I want my x t less than epsilon. Then say, yeah, sure, no problem. If your initial state less than delta, so delta is a function of epsilon, okay? So then that is a perfect fit to the stability condition, okay? So that's for this is a sufficient condition, okay? Oh, sorry, this is yeah, sufficient condition. If this is true, this is stable in the sense of Lyapunov, okay? So let's summarize. So remember, this is sufficient, okay? Sufficient condition. So Lyapunov is giving you a sufficient condition, remember, okay? So we can summarize in exponential stability. So last time we said if this one less than equals to 0, meaning it's always decreasing. Now we specify something like that. So it's upper bounded by minus mu and x squared, okay, x squared. So this specifies actually the speed, decaying speed. We'll see. If this is true, then I know that the system is exponentially stable. Remember, we are talking about the if in here. I want to emphasize second time, okay? It is not IFF. It's not IFF. So it is still a sufficient condition, okay? Sufficient condition. If this is true, then it is also true. So let's do equivalent, okay? So we are here, so this is V dot, okay? This is V dot, okay? This is V dot, V dot. So this is called a negative and definite, negative definite. So this is solution less than always the bound. So then because of the bound, when x goes to 0, it will also go 0. So it will go to the origin, okay? Of course, we assume the origin is the equilibrium point, okay? So it will go to equilibrium point, okay? Equilibrium point. So that's what we have. So the proof, we go through this proof, okay? So this is a V dot, okay? This is a V dot. So we know that the V dot is less than minus V. So it's bounded by the negative of the, so it's kind of like bounded by the X norm square, okay? So remember, we assume the V is upper bounded by rho X norm square. And so we can write, so this is minus xt squared. So less than rho. So if you put minus sign both sides, okay? Okay, so you are going to have changing this greater than equals. Then you divide it by rho both sides. So you have 1 over rho in here, and then you write another way. So you end up with this, okay? So meaning x is lower bounded in here, okay? Lower bounded in here. But remember that your the V dot is less than here, so this is giving. So then I multiply V here, so multiply V both sides. So because minus X norm square will less than minus this, so I put this one in and times V, times mu, okay? So we end up in here, so then I have something V is less than minus, these are all positive constants. This, remember, is V, okay? Remember, it's V. So I end up with what? So I end up with something like, I have a function here. So let me see. So I have a f dot, okay, less than or equals to minus alpha f, okay? So is this familiar? So what is f, okay? If it is equal, then it's, you know that f is e to the power of minus alpha x t. So in fact, this is, oh yeah, here is doing some tricks. So we'll multiply by the integrating factor in here, both sides. So we end up with this. So we're having a term like this. We have a term like this. Okay, so we're not solving differential equation, but we are solving. So then we can write the two terms like this, okay, less than 0. So then you need integration of this one less than 0, okay? Yeah. Basically, we're trying to solve differential equation here. So we have this one less than 0, then what does that mean? So we have these two terms. We didn't change anything here. So in the end, I move everything this side. I'm going to have, this is my V. This is actually my V0, okay? So that is the decaying factor, So then we can say the Vxt is bounded by rho x squared. So in this sense, we can write this way, okay? This is assumed, okay? This is assumed. okay? But it's also lower bounded by the eta x squared. So in the end, I'm writing a left-hand side in a eta x squared because this is greater than that. So this is less than x transpose qx. So this is exactly the same thing like here. This is giving, okay? So then this one will be this one will be like this, okay? So what do I mean? Finally, I can say my x is bounded by the initial size of my x, 0, and there is an exponential function like that. So you have a exponential. Well, this is according to the definition of x. So this is, yeah, I think we have this one. Yeah, this is the exponential stability definition, okay? Definition. So with that, we know that the Lyapunov function, if it can be, so what's the difference? The difference is if somehow you can make your v, okay, x dot, if you can somehow make it less than or equals to, I think they use the mu, minus mu, okay? This is a constant, mu is a positive constant, and this is my size of my x squared. So it can be bounded by minus this one. Then it's exponential stable, okay? So let's run through an example, okay? You have a system like this. You can, AT is continuous for all t. And let's assume Q is I. So now it's a beautiful I, and then Q dot is 0, okay? So let's assume that V is XQ, X transpose Q, X, so Q is I, we'll just leave it. So this is a Q here. So of course, this is satisfy bounded and below. We can say this is a bounded less than 1 times x squared, okay, which is true. Or so this is a upper bounded by 2. You can see a lower bounded by less than or equals to less than equals to 2, but greater than or equals to, sorry, let's say this one is greater than equals to 1 times x squared, okay? So, but anyway, you can see the idea, you have a bound of that. Then you know that in this case, you can simply set V is already x, the x transpose x is x norm square, okay? And so continuity, definitely. So the total derivative, we end up with this, and Q is I, remember. So then we have x transpose AT plus AT. So if this is, so in this case, A transpose T plus AT, remember what is my A? It's minus 1, 1, AT, okay? I think this is 0, is it? Yeah, it's 0. So remember, this is A, AT is, A transpose is 0, AT. You have a minus 1, 1 here. So you add them, what you have left is 0, 0, and yeah, this is a minus, okay, sorry. So you have a 2A left over, okay, in here, all right. So if AT greater than 0, then for all t, the ddt will be less than or equals to 0. That's true, okay? So because it's not going to blow up, there's no way it will blow up, okay? So this whole system is stable, okay? Whole system stable. Remember, okay? Remember, we draw this conclusion. We didn't really get a solution of X, okay? We didn't solve it. So again, I want to write down, we draw this conclusion without solving the original X is a T X, okay? Without solving this, okay? Without solving this. Isn't this beautiful? Otherwise, you need to get phi state transition. You need to do that, and then you check the state transition is bounded. Or that's more tedious. So using the Lyapunov function is a better idea. Okay, this V function, and this V function is nothing but is a concept of generalized energy concept. Okay, energy concept. That's the whole beauty of the Lyapunov function, Lyapunov-based approach. Okay. So we did this. You can see, and even I don't have an exact form of my AT. AT can be anything. Okay. In this case, if AT greater than or equals to 0, then I can draw conclusion it's a stable system. It's not going to blow up for any xt0. Okay. And I can use epsilon delta to challenge, to tell the story of my x of t, okay? So if xt is within a bore of delta, I'm sure the x, for all t, x will live in the bore of epsilon, radius of epsilon. So that's the way we should understand. Okay, isn't this beautiful? Without solving this ODE at all, without solving the phi. Where's my pen? Without solving the phi t0, okay? We don't need that. But in case you have, of course, you can use whether this is bounded, okay? But of course, this is not exponentially stable because you cannot find a norm to bound the v dot. So if you can find this one less than or equals to minus mu x square, then fine, but you cannot because this is actually not possible to bound this. So looks like we are doing very well. So let me summarize what we did. We defined what is Lyapunov function. Okay, Lyapunov function is actually you have the Vx is always greater than 0. Okay, and the Vx is 0 when x is 0. Okay, and Vx can be bracketed by I think they used rho x square. Can forgot maybe mu x square. So this if you find a v of x a scalar function, x is a vector, okay? V is a scalar, okay? Lyapunov function is a scalar. If you can find this, it's called Lyapunov function. Okay. In many cases, x transpose qx can satisfy that. Okay. But there are some other forms of Lyapunov function. So, but you satisfy these three will be okay. And use this Lyapunov function to argue stability properties. It is very energy saving, meaning you don't have to solve the differential equation. You can check you can test or check the stability. Check the stability without solving the ODE, okay? Without solving ODE. So this principle applies to not only linear system, but also for all nonlinear systems, okay? And so this is really powerful, really powerful. So there was a joke, okay? I forgot who made this one first. I remember I didn't invent this. Maybe I invented, I forgot. Saying that in any control literature, say for example, IEEE transaction of automatic control, you pick up any issue, okay? Any issue. Now you can do electronic, right? And you put Lyapunov this thing and search the whole issues PDF, put together a PDF. And from all the text or reference or whatever, you don't see this Lyapunov, this name, okay, in any of the issue. Please tell me, okay? Please tell me. I'm not going to give you cash reward. I can buy you a lunch, okay? So that says Lyapunov is a fundamentally important idea to check the stability of the system. Okay, it's fundamentally important. So we are going to switch to the LTI system, and remember at this point, I want to emphasize, okay, in general, everything is sufficient. Everything is sufficient. Okay, everything is sufficient. Be careful. Don't claim too much. But fortunately, we are going to show you now that for the LTI system, okay, or for linear system, we can establish if and only if conditions, okay? And then the BIBO stability and the internal stability are all connected. So I'm going to go through the slides. So I'm going to ask to see whether you have questions at this point. Let me see how I can.
Can you go to page 10? So here's a,
okay. Okay.
So for the Q, right? So also the rho and the eta will also be positive, both positive, right?
Oh yeah, those constants are positive.
So that means your Q is always positive, semi-definite, right?
Yeah. It could be zero. The lower bound could be zero. Yes, the eta could be zero.
Okay. So if there's positive semi-definite, then the Q is doable.
Yeah. 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 So let me go back to check the quadratic Lyapunov function. Okay. So we talk about generalized energy concept, and so these are the not in equations, but we just say bounded if the variable is bounded, non-zero if variable is non-zero, should be positive. It's zero only when the variable becomes zero. It should be smooth, okay, differentiable. So here is the V. We use the quadratic form of the V, okay? And Q is symmetric, okay? So it's upper bounded by rho, lower bounded by eta. So that's my V. But the low bound could be just zero, okay? The eta could be zero. Okay. But it's fundamentally V is positive, so it's greater than 0. So eta could be 0. Yes, could be. So therefore, you don't really have to find out eta. So differentiation, the change, the derivative is less than 0 means decreasing all. Now this less than or equals less than or equals 0 means non-increasing. It's not necessarily decreasing. If it is 0, that means you keep it there. It's not decreasing, not increasing, right? In nonlinear systems, if this is 0, then we have a lot of other techniques to further quantify the stability nature. So that's called invariant principle. But in here, in linear system, we don't have this issue. It doesn't increase along solutions, okay? Related to Q, so it's the same, okay? The same. What I'm doing here. Yeah, so this d dt, you have 3 terms. That's the first term, the middle term, the last term. And you add together, you are going to see this. So this is a general term when everything is linear time invariant. So you have a qt d dt, but remember when q is a constant, then this term will be 0. Okay. Any other questions you want to ask? If not, we're going to move on. Because the LTI case, do you see my screen, lecture 21?
Yes.
Okay. So final exam, I gave you problem set 8. Final exam is still a take home. And also I'm thinking about you should diversify your reading, not just textbook. You can go to the literature and find out something you feel interested in and present to share with the class. So that counts as like a term project. We can, yeah, I haven't decided whether we should use that as a final exam. I will let you know later. If I give you final exam, probably it's also take home, okay? It's take home, not like the midterm, okay? I haven't graded your midterm yet. So let's talk about, and here we start to put emphasis that everything we talked, it's sufficient conditions, okay? It's called sufficient conditions. But today we are going to go through the LTI system. We're going to show you that LTI system, this is not only sufficient but also necessary. So we're going to talk about this if and only if conditions. Okay. In the end, we are going to talk about BI/BO stability. Okay? So, and fundamental connection to the impulse response. Okay. And all the stability concepts, they should be all connected. But in the linear time invariant systems, all these concepts are equivalent. So in this case, please go back to the Ruggs textbook and read those internal stability and Lyapunov stability. Okay. LTI It's very simple. A is a constant. So in this case, Q is not a time varying, and we have a constant quadratic. So in this case, so you can see whenever you write the T in here, that means you have explicit T in the system, but we don't, okay? Of course, X is still a function of T. Of course, X is still a function of T, but we don't call this explicitly with T, okay? I think you know that. So then partial T here is not just partial here, it's just a ddt, okay? Ddt. So in this case, if Q is 0, dq, because this Q dot is 0. So if you do this partial, it's also 0, okay? So again, this is, because this is constant, then say, oh, upper bounded, then I know that it's linked to my maximum singular, maximum eigenvalue here. Okay, maximum eigenvalue. So if my maximum eigenvalue, my Q, or remember Q still satisfies Q is Q transverse, okay? So you can see the eigenvalue is connected, okay? So then as a minimum eigenvalue of this one will be greater than or equals to Q, yeah. Okay. Is this possible to be 0? My answer is yes. So then I hope the V dot is less than 0. Then that means I have A transpose Q, QA is less than 0. So this is actually called the Lyapunov inequality. Inequality. Okay, Lyapunov inequality. Because this is induced from the Lyapunov function. Okay, A transpose Q and QA is less than 0. What does that mean? Okay. That means A transpose Q plus QA is NSD. NSD. Okay. So you have freedoms to choose. You have freedom to choose. You have freedom to choose your Q. It doesn't matter. You can choose any Q you like. Okay. So Q is n by n matrix. Okay. The ideal case is I, right? It is I. So in other words, we probably find out a way to tell if the system is stable. We probably just simply say, oh, if A transpose plus A is NSD, it's NSD. Okay. So again, without checking all the eigenvalues. Okay. So we call this minus W, then we call W is a positive, and it's positive definite. Okay, so the minimum of, if the minimum eigenvalue of a matrix is non-negative, okay, this is non-negative, then W is called positive semi-definite, okay, PSD, positive semi-definite. Okay. So what's the stability? If you find a Lyapunov function, that implies stable in the Lyapunov sense. So that means this one, the W is a minus, so is W, this one, okay, the minimum of this one is not negative, is not 0, then it is exponentially stable. Exponentially stable. Exponentially stable meaning your x will go to 0. Okay, will go to 0. But in this case here, we simply say lambda minimum minus AQ minus QA greater than equals to 0. So that one, you can only draw the conclusion of stable in the sense of Lyapunov. If you without the equal sign, then we call this is stability in the sense of Lyapunov. So nice. So the procedure of checking is you choose IQ greater than 0. You have infinite choices in here depending on the convenience. Usually you start with I. Okay. Then you compute matrix W. Then you check the W's if it's PSD. Okay, then it's a stable. The original system is stable. If this is a PD, so when I say a square matrix greater than 0, that means this matrix is a positive definite. Okay, positive definite. So that's the way we check. We have a procedure to do that. So did you see that if we want to do traditional way, what we do, we need to do a 5t sigma, which is actually you are going to do a E t minus sigma, right? So then this is non-trivial, is very difficult to do. So then should see whether this is bounded. That's difficult. So you should use Lyapunov. Based on Lyapunov theory, LTI, then we end up with checking a matrix W is PD or PSD. Okay. So again, we avoid solving the differential equation. So this is called the invariance theorem. So it's kind of interesting. We can perform some people may say hey, I have a quick method. So people may say quick, but unfortunately it's dirty. Okay, quick and dirty method. Okay, but here I'm going to tell you it's not necessarily true. Okay, necessarily true. So I have theorem saying that I have this one. So somehow you can find out transformation here. Okay, so you can find a matrix C to C transpose C makes that one as a Lyapunov function. Okay, and so then you say, oh, if AC is observable, then everything is exponentially stable. So that's an interesting way to look at this. Okay, so let's try to prove it. So if you have a Lyapunov function, it's already implies stable in the sense of Lyapunov. So then we do. So remember, this is W. Okay, and W is positive definite. Okay. So then we assume W can be expressed on this. So remember, I can write down my state transition matrix like that. So then we're going to write something like this. So this is the initial state. So remember, this is what? So this is nothing but we can write C. This is a norm square. Okay, norm square. So it's like a y transpose y is y square. Okay, the same. So this is a negative sign here. So I integrate both sides. We are going to have basically I integrate this guy. I'm going to get this, and then it's equivalent to I integrate this, everything here. Okay, everything here. So that is always positive. Okay, because you have square here. So then in this case, stability means the eigenvalue of A, the real part is not positive. So you can find x0 such that xt does not approach to 0. That means, okay, eigenvalue of lambda of A is 0. So that is meaning you have a root in here. It's a complex conjugate on the imaginary axis, or you have origin. So the real part is 0. So that means you do not go to, so this is a real part, this is the imaginary part for the eigenvalues. But for the face, like x1, x2, you have two-dimensional system. That means you are going to have something like this, okay? So this is circle. You are not going to decrease to, no, you don't do that. So you always have this one. It's called a sinusoid, okay? Sinusoid, oscillatory, okay? So that's, we know, okay? So in this case, if I set my x0 as my vector and put x0 both sides, so this is the eigenvalue. So it must be equal if v is x0 is not 0. So that will give us e to the power of at, okay, this one, okay. It's also e to the power of lambda t in here, so, okay. So in this case, we know that we can write or return back from the previous integration. So in this case, we can write lambda t in here, okay, lambda t in here. This is a matrix. Then we can pull out this lambda sigma here, okay. And you have C times V in here, okay, So then you come out with C times V is still the same. So you integrate. So you have this integration here. So in other words, you are getting a T in here. So times this. So that means you have something going up. So this is always positive. This is all. So it's always minus this one here. We know that is less than, is lower bounded by this. So in this case, I know that my xt is always, of course, greater than 0, but less than 1 over lambda, this one, okay? And we are trying to apply our, definition, okay, definition. So if this is true, then I want this one to be 0, okay? So if this is 0, then that means this AC is not observable, okay? It's not observable. So we have to say that all the eigenvalues must have negative real parts, okay? That's the necessary condition to have a stable system. And if this is strictly less than 0, then it is exponentially stable. Okay. And the invariant means whatever Q you put there, and so you put any negative semi-definite matrix there, you always get observable for negative definite. So in summary, let's go into this. Okay. So of course you are giving. We are talking about how to check the stability of AX. Okay. We assume that W is this is strictly PD, positive definite. This is negative definite. Okay. You can find them to satisfy this relationship. Okay, this relationship. So here is talking about there exists WQ, okay, to satisfy that, if you can find this. So then we know that the overall system is exponentially stable. Okay, exponentially stable. And there is no eigenvalue at the origin or at the imaginary axis. Okay, no, because this is strictly decreasing. Okay, strictly decreasing. So we can say in the end, the V dot is strictly less than 0. Okay. So it's keep going down until to 0. So in this case, we know if we can find Q and W, then we can know that A has all eigenvalues with negative real parts. In this case, if A has all eigenvalues with negative real parts, it's called Hurwitz. So in the future, when we say A is Hurwitz, means there's no eigenvalues on the imaginary axis. It's all in the right half plane. Sorry, left half plane. Yeah, left half plane. Left half plane. So this is a very important concept. We exclude those 0 in the origin, that kind of argument. Okay. So you may wonder what we are doing here. Okay, I already told you we don't have to solve the differential equation using Lyapunov function. Lyapunov. Okay, using the Lyapunov function, Lyapunov theorem, we can check the stability without solving this. But it may happen that you still need to check the eigenvalues of that. So what if I know eigenvalue computation? If I can check eigenvalues of A matrix, I know that the stability is easy to check if they live on this left half plane, right? So we don't want to do this, don't want to solve this. We don't want to solve eigenvalues of A. We only need to do algebraic matrix differential equation, matrix equation. So this equation has a familiar name. You can guess it's called Lyapunov function, Lyapunov equation. Lyapunov equation. Okay. In MATLAB, there's a this command. You give a Q, or you give a W, they can get you a Q. Okay. So you give W that is a positive definite, and then in the end, after you solve the Q, you check whether Q is positive definite. If yes, then I can tell that A matrix is Hurwitz. Okay, all eigenvalues with negative real parts. Okay, so now isn't this beautiful? Yeah, we step back. In the end, we just need to solve an algebraic matrix equation. Giving A, giving W, solve the Q. Now, sometimes you have freedom to choose the W. Okay, so it's a very simple procedure. So then you can check the original system, LTI system stability or not. This is beautiful. Okay. So interestingly, it's also possible we can prove if we assume A is Hurwitz, okay? So how I pick up the Q? If I pick up Q as something like this, okay? Giving any W, put it here, okay? They will construct the Q. Then we have a unique solution. This Q is the unique solution to this Lyapunov function, okay? This is beautiful too. Beautiful too. And now you roughly can say that doing this is so hard, but solving this is relatively easy. Okay. Remember, I also put Q is Q symmetric. Okay. Symmetric. And so then you only have half of the. It's not n by n. You only need n plus 1 divided by 2 equations to solve. Okay, so it's not so hard and numerically. Okay. So it's not n by n. It is n. It's a 1 plus 2 plus until n. Okay. Then it's n plus 1 divided by 2. So I want to ask. We started with Lyapunov generalized energy, but in the end, we are playing with all the matrices here. So let's verify Kalman's famous Kalman filter you heard about. Kalman's filter say that make physics right. And the rest is mathematics, okay? So here, everything we are playing here, they are just math, okay? Or you just add another picture in here, x is x, so math. But what is the physics? This is the physics, okay? That's your generalized energy. That's energy. Make sense? This is your physics, okay? So a lot of people get lost at this point. So what are you doing? This and that, you know. I told you in the last slide what we are doing. What we are doing is try to avoid solving differential equation, avoid solving the eigenvalue of matrix A. These are very expensive and difficult. And we step back and eventually borrow Lyapunov's concept. We only need to do a Lyapunov equation solution, and we only need to solve unknown equations like this. Okay. Okay, so we're almost there. So we have a proof. First half of theorem has been done. So it's a all if and only if actually. So we have seen this already, right? So we have seen this already. Okay. So conversely, let's see how we argue. Let's assume that A is already Hurwitz. That means lambda I A, the real part of that is greater than 0, not greater than or equal to 2. Okay, greater than 0. So it's the unique solution for that. Okay. Furthermore, if this positive definite, then I can guarantee Q is positive definite. So, proof this half. Okay. All eigenvalues are negative real parts. Then integral exists. Q as given by the theorem like this. Then ATQ becomes something like that. It's you can bring A inside because A is nothing to do with T, so we can always write it this way. So because Q like that. So and this one is 2 terms. Remember, we have A. This is remember is my state transition here, and this is derivative here. Let's because this is a derivative in here, so let's just bring this one, the overall this one here, and do infinity to 0. This will give you minus W, because when t is 0, this is I. T is 0, this is I. So this is minus. But if you put infinity in here, because eigenvalues here are negative, okay? No 0, not on the imaginary axis. Therefore, these terms will be 0. So it's kind of 0 minus W, okay? 0 minus W, done, okay? So we have argued that. So this is true, okay? This is true. So it's very interesting to argue that this Q must be unique. If you say, oh, we got another Q0, it's also a solution. Then you put this one, you know, this is 0. Then you put this one, it's also 0. You do this, you integrate that. So this will give you, so what do you get? Because this is all 0, okay? They're all 0. Okay? So then that means the whole thing from 0 to infinity, if we put infinity, this is 0. This is also 0. So it's minus this one, okay? Minus, so this is minus Q0. And it is 0, okay? It is 0. So therefore, Q is Q0. So that's why we proved that the Q is unique, okay? Yeah, you can see the swap Q0 minus Q. Yeah, it's because the minus sign. So we can stop here. Okay, we can stop here. And we're going to continue to discuss these slides in the next lecture on Monday. Let me open to see whether you have questions. Do you have any questions? I don't hear you.
I'm okay for now.
I think this is actually simple, and those are the basic facts. Okay, now I can see you. Oh, you are left. You are alone. Okay, so I'm going to say goodbye to you and take care of yourself and keep safe, and see you Monday. Okay. Monday we are going to have a help session as well. Okay.
Okay.
Bye bye, Jack.
Goodbye. Yeah.
Oh, everybody's here. All right. Bye bye.
Goodbye.